Okay, now we come to distributed ray tracing. So distributed ray tracing is where we're going to start sending more rays. Now is when our time constraints are going to get really terrible in terms of how slow are things going to get. So let's consider our first case. We'd like to get soft shadows like this rather than hard shadows. How are we going to get this to work? Like, where are we going to send rays in order to get our soft shadow to work? So here's a picture. Here's our primary ray. We hit a point. Now, instead of considering our light to be a point light source, we're going to consider our light to have an area, right? And that's indeed where in the real world, if you see these are called penumbra, right? In the going from full shadow to partial shadow, this is because real lights in the real world are not point lights, they have an area to them. So we're going to now sample across this light and say which fraction of the light is blocked. Now, in an ideal mathematical sense, we wish we could run an integral over all of this space over this light and figure out which fraction is blocked. In a ray tracer, we typically sample this with finite rays, right? We send rays to some number of samples of this thing and then calculate an estimate for what fraction is in shadow. But the question becomes, how many of those rays do we need, right? Is 5 a good number? Well, now let's go back to our picture. So in this picture, we went from not in shadow to all the way in shadow, right? From 0% to 100% in shadow. Let's say this was 100 pixels to get from here to here. So that means I have a pixel, which is 100% in shadow, a pixel at 99% in shadow, a pixel at 98% in shadow. So to get a nice smooth thing like this, then I'm going to need at least 100 rays so I can get everything from 0% to 1% to 2% to 3% as I slowly get more and more into shadow. So 5 rays isn't going to do it. If I actually did it with just 5 rays, I'm going to get clear bands of like, 100% in shadow, 80% in shadow, 60% in shadow. I don't want to see those bands. So it actually takes quite a bit of rays to get this smooth, right? So this isn't going to be 5. This is going to be 100 to get something like this, where it's a nice smooth thing. Now, do I really need 100? Can I tell the difference between 98% and 99%? Okay, I'm not sure. But it's more than 5. It's less than 1,000. It's some number that makes your picture look smooth in the end. So it could be a lot of rays in order to get soft shadows to work right. The code is easy to write. Like whatever, I have the code to intersect a ray, whatever, just write a loop, send 100 of them, add it up, who cares? Yeah, but 100 times on your running, so okay, this is another reason that it's waiting overnight to get your picture. So we can also do glossy reflections. Same kind of idea. We're going to distribute rays across a range of directions. I just told you the answer. Oh well, no poll on this one. So if I want to get this kind of reflection, which isn't a perfect mirror reflection, but is instead a smooth, how do I want to say, a glossy reflection or a partially blurry reflection like this, rather than a perfect reflection, right? This is a perfect reflection up here of this light source. Here, this is probably a reflection because I can see the square shape as opposed to a specular highlight calculated with the Phong shading that we did before, right? This is probably reflected rays up to this white piece of box up here. So this is perfect reflection. We see this is nice and sharp boundaries here with the blurry. What do? Okay, we're going to send a lot of rays now. So for a perfect mirror reflection, we only had to send 1 ray. So that gives you a picture that looks kind of like this. And we can see our little test object has perfect boundaries. If I want to get slightly glossy, I'm essentially going to send rays inside all of these directions and add these things up. So we saw a diagram like this before, right? This is a diagram that we saw before when we were talking about how to calculate lighting with a specular reflection. So now we're going to actually send rays, and how much weight are we going to give each ray? Well, that depends on the direction. So if there's more light that's getting reflected in the specular direction, the mirror reflection, we're going to give that more weight. And then this is going to be a lobe, which has this kind of shape that we saw before, and we're going to add up those. Now, again, it might not be 5, it might be 100, depending on how big the range is. Here, the blurriness looks like maybe it's only 5 or 10 pixels across, so maybe I only need 5 or 10 rays in order to represent that well. Here, the blurriness is a larger range, so I'm going to need more rays to represent it well. At the limit, we could have diffuse objects. Now, for a diffuse object, if I really wanted to get the reflected light from all directions, I would have to send rays in every direction. So this would be thousands of rays to sample all directions, all everything. Nobody does this. You don't say, I have a diffuse object, and then I'm going to send rays in all directions. You just say, I have a diffuse object, let me calculate n.l, and I'm done. This would be considered quite hard. So this is common and easy in a ray tracer. Just one ray is my cost. So we see lots of perfect reflected mirror balls in ray tracers. Diffuse object, also no problem. We see these in both kinds of renderers, ray traces and triangle renderers. This one is a real pain. I need hundreds and hundreds of rays in a ray tracer, and it's not easy to get in our triangle renderer. So this is somehow the most painful thing to get in graphics in terms of efficiency cost. Because I have to send a lot of rays in a lot of directions to find out how to get this reflection. So here's the distributed reflections we were just talking about. Here's another example, right? So here's our stained glass window, and you can see it's more blurry if my rays went further because the angles spread out more. But the calculation's all the same in terms of sending the rays. We can also do this for like shower door, right? I have a glossy, not perfectly transmissive refractive object, right? So this kind of glass that I wanted to go through and get fuzzy. Same idea. My refracted ray, I'm going to send multiple rays out. This is the one we saw before with the light, right? We're essentially sending rays to estimate an integral over the lighting area. Okay, this is the same kind of effect, right? Hard versus I've got this softer thing. There's more effects that we can get. Somebody asked weeks ago in class, like, if I wanted a real camera with depth of field, where does that come from? Well, in a real camera, I have a lens, and this lens doesn't focus perfectly. But now I'm shooting rays. And in fact, this is what they do when they do lens design to try to figure out how to get them to focus in the first place. We could put a lens into our rendering and then send rays, multiple rays through the lens, which would have different ways that they interact with the world. So for each pixel, instead of a single primary ray, we'd send a set of rays through the lens and then find out the average of those colors that came back. This would be another kind of distributed ray tracing. Same thing with time. If we wanted motion blur, rather than treating the world as frozen at a single instant of time, we would know how our objects are animating, and we would say this ray is sent at time t, and this ray is sent at time t plus 10 milliseconds, right? And then we would distribute a bunch of rays over all of this and add it all up. And then that would get us to pictures like this, where we get some kind of motion blur. Of course, is there a time cost? Yeah, it's gonna cost you. It's gonna get slower. When we talk about movie studios needing a giant room full of computers to go calculate all their ray traced images, to go calculate each frame of the movie, right? A frame of a movie might take an hour to calculate, right? And so I got 24 frames a second of movie, I got to go calculate an hour for each one. I get a whole room full of computers to go calculate this stuff. So yes, it might take time, and it does if I want to get all of these effects into my rendering. So here's another thing which we might want to go calculate. It turns out that we've been pretending in graphics so far, even in our ray tracer so far, that when light hits a surface, it's going to bounce off of that surface, or it's going to somehow cleanly transmit through the surface. But it turns out lots of surfaces have subsurface scattering. What does that mean? That means that the light actually penetrates the surface, hits small pigments and other things inside the surface, bounces around, right? And some of it has a short path and bounces around and comes out, and some has a long path and bounces around and comes out. We could simulate all this stuff with a ray tracer, right? And so human skin behaves this way. Lots of different materials like rocks behave this way, right? The light goes in, bounces around before it comes out. This is also adding complexity and cost. This was way too complicated for normal ray tracing. So I would say in a normal ray tracer, nobody simulates all these bounces. This would be insane. This is getting too much. So if you're doing research on it and trying to see how it works, people might do it. But they're going to use some kind of hack to try to shortcut this, because this is just too much bouncing around. These kind of effects, people really do this with accelerations to try to make it faster. right? Try to get your code efficient and things like this. But people do these kinds of things. This is too much. We saw this picture, I think, sometime earlier in the class. So here's the light just bouncing off of the white stuff inside, and this is different amounts of subsurface scattering to get it to look more like milk. And this really was done by doing the bounces inside, but this was from a research paper talking about what subsurface scattering can get you. Here's an example with a jade statue. I can't remember if I showed you this picture before. Here it is. If it just bounces off of the front surface, it looks more like concrete. And then this looks supposed to look more like a jade statue. And the amount of subsurface scattering will give you a feeling of sort of how big is this statue. Because for a small statue, things get much more bounced around inside. And for a big statue, if this was in the real world big, then the light wouldn't penetrate as far and it would look closer to this, right? So you can get effects that matter. Now I said that people don't do subsurface scattering. It's not true that we don't use subsurface scattering in graphics. It's that all this bouncing around in the ray tracer, this is just too much computation. So what do? There's going to be some hack that basically says if a ray hits my object, which is supposed to have subsurface scattering, I've done some pre-calculation of the statistics, and like 20% of the time, the ray comes back out not too far away. And another 20% of the time, it comes out a little bit further away. So how about we just store those statistics and like just go ahead and like when I hit here, shift that thing over and like start doing calculations from there or something like that, right? So that's a simple way to say it. There's a bunch of research on how would we do this approximation in a fast way. So I'm not saying there's no subsurface scattering. It's actually quite common now, but it's not calculated in this way is what I'm saying.